Hi, and welcome to Chapter 7, Section 3.
I've been wanting to do an intro like that for so long, and I finally got to do it. All right, so in this last section of Chapter 7, we are looking at sampling distributions with sample means. So just like our previous sections, we would, be taking all the different sample sizes out of a population of a certain size, and then within each of those samples, we would look for that sample mean. And then out of all the different samples, all the different combinations of those samples, and each of those means, we would be able to put together a distribution of just all those sample means. So just like our sample proportions, we can describe the center, the spread, the shape, all that good stuff. So in the center, the mean of our sampling distribution, so the center of our sampling distribution, would be equal to the mean of our population. So our population parameter would be mu, whatever number that is, and that usually is given to you in the problem. And so our center of our sampling distribution would be equal to that. Because if you think about it, when you're taking a bunch of samples from a population, whatever the population mean is, when we take each of those samples, the mean should kind of average out to be what the population mean is as well. When we talk about the spread of a sampling distribution of sample means, the standard deviation of the sampling distribution would be the standard deviation of the population divided by the square root of your sample size. So if you remember, the bigger sample sizes we have, or the bigger our sample size, the more consistent our data is going to be compared to the population data. So if it's more consistent, that means the spread should be less, because if it's less spread out, you have more consistent data. So when we divide by the square root of n, that decreases our standard deviation of the population, saying this is going to be a smaller number. So that's why our standard deviation of a sampling distribution is always smaller than the standard deviation of the population. The only thing is, in order to use this formula, we have to make sure we have independent samples. So when we talk about each sample being independent from each other when we pick it, or if we are sampling without replacement, something like picking people out of the population or something like that, then the 10% condition must be satisfied. So this also works for our sample proportions as well. We talked about the 10% condition there being the sample size must be less than 10% of the population. Finally, when we talk about the shape, we basically just want approximately normal, because then we can actually use our normal curve calculations to calculate probabilities and whatever. So there's a few ways we can do this. So first, if our original population data is already normal, then our sampling distribution shape is also going to be normal, which makes sense. So if you're pulling data in the form of samples from a population that's already normally distributed, then when you pull those samples, you should end up with a normal shape as well, because you're pulling from a population that's already normal. And it just has to be approximately normal. So the way we would know this is the problem would have to tell you that the original data is approximately normal. So that's how you'll know, okay, my shape for the sampling distribution is also going to be approximately normal. Let's say our population data isn't approximately normal. So if it's skewed or we don't even know, then there is a way to get our sampling distribution to be approximately normal. So the method is called the central limit theorem. So central limit theorem basically says, if your sample size is large, then your sampling distribution is going to be approximately normal. Because if you have large enough of sample sizes, that means, remember, your data should be more consistent. And because we're pulling all the different combinations of that specific sample size, it actually ends up being approximately normal. It's kind of cool. So even if your population data started out as skewed, it'll eventually, when you pull those sampling distributions, then it'll become approximately normal. So when we say large sample sizes, there's no set rule for this. We basically just need large sample sizes, but depending on the textbook, it'll say different numbers. Our textbook says 30. 30 is considered large. So when your sample size is 30 or more, this is considered large. And again, this is not a set rule. So even if you saw a problem where like the sample size was like 27, 25. This is considered large as well. So again, no set rule. So as long as in your explanation when you do the problem, because we have to check our conditions every time, as long as you say we have large sample sizes, that counts as you checking to make sure n was 30 or more, or large in some form. So, so you would say something like the central limit theorem says because we have large sample sizes, our sampling distribution shape is going to be approximately normal. All right, so in this example, I want to kind of show you a difference in the type of questioning. That way you can kind of see like how to answer each type. Because this is going to be very similar, our process to calculate probabilities is going to be very similar to how we did normal probabilities to begin with. So first of all, we have scores of students on the ACT on a recent year had a normal distribution. So right off the bat, they're telling us this is a normal distribution with a mean of 18.6 and a standard deviation of 5.9. So my two questions. What is the probability that a single student randomly chosen from all those taking the test scores 21 or higher? My second question, now take a simple random sample of 50 students who took the test. What is the probability that the mean score of these students is 21 or higher? So this is where I wanted to show you the difference between the two types of questions. So in the second one, we are specifically looking at like a sample of students. So this would be where we talk about sample means and the sampling distribution for that. Whereas in the first question, we're just looking at one person at a time. So with one person, you're not looking at a sample. This is how we did probabilities back in chapter 2. So they already told us it was a normal distribution, so the mean and standard deviation remain unchanged for a single student. So just like how we used to do it, we would draw our normal curve, label the mean and standard deviation, and shade in, they're asking about 21 or higher, so we're going to shade 21 and onwards. And then find our z-scores, find our probability, answer with words. So finding my z-score of 0.407, and then using normal CDF in my calculator just to go faster. You can use the table if you want, but I end up with a probability of 34.2%. So now, for part B, if we look at the second question, now we're taking a simple random sample of 50 students. So now our sample size, n, is 50. What is the probability that the mean score of these students is 21 or higher? So now, because I have a sample size, then I know I'm going to have to deal with the sampling distribution and set up my normal curve that way. So because my population data was already normally distributed, my sampling distribution is also going to be normal. So when we look at the spread, our mean and spread of our sampling distribution, the spread, we would use our sampling distribution formula, which is the standard deviation over the square root of n. So when I do that, I get 0.834. But of course, before we can actually use that, we actually have to check, like, does this even work? So we need to check that we either have the independent samples or the 10% condition applies. So here, because we're sampling people, when you pick your samples, it's not like you can put them back in, so we're not replacing them. So that means we don't have independent samples. So we move on to our 10% condition. So with the 10% condition, this applies because we can assume there are over 50, because our sample size was 50, times 10, which is 500 students taking the ACT on a given year. So our sample size then makes it less than 10% of the population. So the 10% condition applies. So we are allowed to use this formula to calculate the spread, the standard deviation of our sampling distribution. Then our mean would be the same mean as the population. So our mean is just going to be the 18.6 still. And lastly, our shape is approximately normal because our population is normal. So I can draw my normal curve, label my mean of 18.6, my standard deviation, my new standard deviation of 0.834 because that's what I got from dividing by the square root of n. And then we are still shading 21 or higher. So we're finding this probability now. So finding z-scores and using normal CDF again. So I ended up with a z-score of 2.878, and when we did the probability of that happening, we get 0.2%. Whoa, way different than what we had originally when we were just looking at one person at a time. So now, basically, if we're trying to pick a sample of 50 students, for that sample mean to be 21 or higher means that in that entire sample, you need a bunch of high-scoring students. So having that happen is a lot less likely because, in a sample of students taking the ACT, you're going to have a mix of good and bad students. So getting a sample mean of 21 or higher is a lot harder to do. So that's why it came out to such a low probability, 0.2%. All right, so of course we answer in words as well, and then that's it. So as you do these problems, make sure you are reading the question carefully to determine whether they're asking about a sample mean or, just overall population for a single student, single item, whatever it is. That's it for this section. Thanks for watching. Bye.